Hi, I'm Koyong Hu. This is my IA application videos for X376. Today we are going to go through problems related to Turing reductions. We want to prove the following language is undecidable. The language L is a set of Turing machines, where the language of these Turing machines is decidable by a Turing machines. As we know, for an unrecognizable language, we can always find one or more Turing machines that recognize this language. So the question is equivalently asking us whether we can build a Turing machines that decides whether a recognizable language is decidable or not. And the answer is no, and we need to show the reasons. To show that L is undecidable, we can construct a Turing reductions from an undecidable language that we have already proven to the language L. So our aim is to build a Turing reduction D from L epsilon hot to L using a black box H that decides L. The black box H is called oracles. So how to build the Turing reductions? A trivial idea is just put the input of D directly into our oracles and return whatever is output from H. However, this is definitely not correct, since H and D does not recognize the same language. So we need to modify the input of our oracles. Say we change it to H M prime, such that if M halts on epsilons, D and H should accept. And if M loops on epsilons, D and H should reject. In this case, we want to construct a function M prime such that if M epsilon halts, M prime recognize a decidable language. Otherwise, M prime recognize an undecidable language. So what is the decidable language and undecidable language here? Actually, we can pick the languages that fits in these criteria. For example, I picked the set of all strings to be the decidable language here, and L epsilon hot to be our undecidable language here. Let's start from the first part. We can directly simulate M epsilon hot and check whether it halts. If it does halt, M prime should directly returns accepts. In this case, M prime will accept the set of accept all strings and recognize the set of all strings. Otherwise, M prime should recognize L epsilon hot. Let's recall what is L epsilon hot. It's a set of Turing machines such that these Turing machines halt on input epsilons. So the input of M prime should also be Turing machines such that when it simulates T epsilons, if it does halt, M prime should return accepts. Otherwise, M prime will loops as T epsilon loops. However, these Turing reductions is not correct, since we assume that if M epsilon does loops, we should jump to line 7 so that M prime will recognize L epsilon hot. However, actually M prime will stuck as M epsilon loops. So how we deal with it? We use a strategy called dovetailings, where we simulate M epsilon and T epsilon simultaneously. This is done by alternating between the simulations of T epsilon and M epsilons. So if M epsilon halts, our M prime will return accepts. If it does not halt, we check whether T halts. If T halts, we also return accepts. So if any one of the simulation halts, we immediately return accepts. Now we get our final version of Turing reductions. Note that M prime accepts if and only if either M or T halts on epsilons. Now we need to verify that our Turing reduction thus decides the language L epsilon halts. If M epsilon does halt, then M prime will return accepts, no matter what input it takes. So M prime will recognize the set of all strings, which is a decidable set. So M, H, and D will accept as expected. However, if M epsilon loops, then there are two cases. The first case, if T belongs to L epsilon halts, then T epsilon does halts and M prime will accept. However, if T does not belong to L epsilon halts, T epsilon will loops, and since both T epsilons and M epsilons are loops, M primes will loops. In this case, M prime will recognize L epsilon halts, which is, we have proven, an undecidable language. So both H and D will reject, as we expected. So now we have verified that D is indeed a return reductions from L epsilon halt to L. Since L epsilon halt is undecidable, L should also be undecidable. This problem tells us that we cannot build a Turing machine that decides whether a recognizable language is decidable or not. And that's all for our review. Thank you.